The last couple times we've taken notes, we have talked about what electricity is and how it flows. In certain parts, we briefly mentioned electric circuits. Now we're going to start focusing on circuits a little bit more. There's two basic ways to wire a circuit. We can wire them in series, which means one item right after the other, or in parallel, which means we have little junctions between each one, and the electricity can pick several different routes to get through the circuit. From this point on, anything and everything is going to be considered to be a resistor if it's not the battery. So we can have a toaster, a microwave, an electric stove, a coffee pot, a light. All kinds of things are going to be resistors because they require resistance to work, and we look at them in an electric circuit based on how much resistance they require. As we look at these electric circuits, we can consider them to be like the highway. In a series circuit, that's like if we're on the interstate and there's not very many exits to the interstate, so we have to all follow the same path. Well, if at one point in the interstate there's an accident, that blacks up traffic all the way back to the beginning and no one can get through. That means if we break one light bulb in this circuit, all the electricity is going to get backed up and our whole entire circuit's not going to work. But if we look at the parallel circuit, we have a bunch of small little side streets. So even if there's an accident in our way, we can still get around and get to where we need to be. So if we were to break one light bulb, all of the rest of them would still work. In many circuit problems, we're going to just be given a picture and be asked to calculate things from the picture. So we need to know what the symbols in the picture stand for. The first thing we'll always have is some kind of power source. In most cases, it's a battery. In the battery, the long end is the positive end, and the short line is the negative line. So in this particular example, there would be two batteries connected to each other. Sometimes we will see that positive and negative are already labeled for us, and that usually only happens though if we only have one battery. Another thing they're always going to have is a resistor. The symbol for a resistor is just kind of a squiggly line, okay, to show that there's some kind of obstacle for the electricity to go through. For both the battery and the resistor, we have to label how big they are. So in terms of the battery, we need to know the voltage, and in terms of the resistor, we need to know the ohms. Two other important symbols are the voltmeter and the ammeter. They're going to measure the voltage and the current in or around our circuit. We'll look at those more in depth here in a second. A fourth very, very important symbol is the one for a switch. This particular example is an open switch, which means no electricity is flowing through this switch. If we were to close this switch, that's like turning on the lights. So closed equals on. And a closed switch would look something like this. Okay. Another common example that we'll see is the symbol for a light bulb. If ever there is a symbol that you don't recognize or that's not included on this list, you can also refer to page 731 in your textbook. Now let's look at the voltmeter and the ammeter a little bit more in depth. When we put a voltmeter in, we're going to measure the voltage. We already know the voltage of our battery, so we don't want to put our voltmeter right next to our battery. We want to know what happens to the voltage after it goes through the resistor, which is kind of like an obstacle that slows it down, makes it lose some energy. So we wire it so that it goes around the resistor. As for an ammeter, which measures our current or our amperage, we want that to be connected right into the circuit so that our current actually goes through this ammeter. If we were to connect it in the same manner that we connected the voltmeter, then we would not be getting a correct reading. When we draw a circuit, we start at the positive end of the battery and follow it along and draw everything that we see. As we draw the diagrams, even though our wires are not square, we draw them as they're square to help with clean lines and not get confused on where the lines are going. We want them to be as straight as possible, so we're going to just square them off even though they're not really square in the actual wiring system. In both of these examples down here, we have an open switch and a battery and two light bulbs. The example on the left is a series circuit, meaning the two light bulbs and the switch are lined up one after the other. And the second example is parallel. When you wire your motorboats, you will want to wire your motor and your switch so that they're in series. If the switch was not in series with the light bulb, then that switch could not control that light bulb. In the series circuit, the resistors are wired one after another. Since they are all part of the same loop, they each experience the same amount of current. However, when we look at voltage, they share the voltage from this battery. Okay. So the total voltage has to equal the voltage from light bulb 1 plus light bulb 2 plus light bulb 3, while the total current will equal the current in light bulb 1, in light bulb 2, and in light bulb 3. But how do I know which one's light bulb 1, light bulb 2, or light bulb 3? The trick is we start at the positive end of the battery and follow it along. So this is light bulb 1, 2, and 3. I just used an R to say they provide some kind of resistance. As the current goes through the circuit, the charges must use energy to get through the resistor. So each individual resistor will get its own individual potential voltage. We call this a voltage drop because we lose voltage as we go through each resistor. You can kind of think of it like if you were to try and complete an obstacle course. Resistor number 1 is your first obstacle. After you've completed that obstacle, you're a little bit tired, but you still move on to obstacle 2. Or resistor 2. Again, after you're done with that, you lose a little bit more energy. But you can still carry on to resistor 3 or obstacle 3. If we were to put too many resistors in the way, our power supply would not be able to power all of them. This is just like if we put too many obstacles in the obstacle course, you may not have enough energy to make it to the end. When this happens, we tend to consider this to be tripping a breaker. Your house is wired with breaker systems so that if we're pulling too much electricity through the same spot, everything connected to that breaker will turn off. Now we can take the two equations that we looked at on the previous slide and combine them with our Ohm's law equation to come up with an equation for resistors in series. Because the current was the same in every spot, and the total voltage was the voltage of resistor 1 plus resistor 2 plus resistor 3, that means that our total resistance in a series circuit has to be resistance 1 plus resistance 2 plus resistance 3. If there were more than 3 resistors in this series circuit, I would simply keep adding them all together until I incorporated all of them. And because we know physicists are lazy, we don't like to write things out, and we like to simplify them as much as possible. The simplest way to write this equation is R subscript S, which stands for series, is equal to the sum of all the individual resistors. So we're going to use an I for individual. If you don't remember, this symbol right here is a Greek letter sigma, which means sum or total. Depending on the resource that we're looking at, they may also ask us for the effective or equivalent resistance. Those two words also mean total. Now let's try a sample problem. A series circuit is shown at the left. So the first thing we need to do is we need to go around and label our resistors as resistor 1, resistor 2, and resistor 3. Okay. The first part of our question says, what is the total resistance? We know that R total equals R1 plus R2 plus R3. Based on this given information on the left side, we know that R total is going to be equal to 2 plus 3 plus 1, which equals 6 ohms. Part 2 of our question says, what is the total current? Current, we know, is based on Ohm's law that says voltage equals current times resistance. Because we want the total current, means we're also going to use the total resistance. Okay. Our diagram tells us that we have a 12-volt battery. We're solving for current, and we just calculated our total resistance to be 6 ohms. To get I by itself, I'm going to divide both sides by 6, and that gives me 2 amps equals my current. Part C of the question asks us to find the current across each resistor. Well, we said before that the total current equals the current in resistor 1, which equals the current in resistor 2, which equals the current in resistor 3. We calculated our total current to be 2 amps. So, each resistor must have a current of 2 amps. The last part of this problem says, what is the voltage drop across each resistor? Our hint for this problem is to apply Ohm's law to each resistor separately. We know that Ohm's law says voltage equals current times resistance. We calculated before that our current equals 2 amps. And our hint is to do each resistor separately. So you can see that over on the side I have color-coded each of the resistors. So let's start with our blue resistor. Voltage would be equal to 2 amps times 2 ohms. So we get 4 volts. Next, if we calculate our red voltage, we get 2 amps times 3 ohms, which equals 6 volts. And then for our green one, we get voltage equals 2 amps times 1 ohm, which equals 2 volts. If I were to take and add up all of these numbers, I get a total of 12 volts. That is exactly what we started with from our battery, is 12 volts. So that must mean that the individual voltage drops add up to the total voltage. In the next video, we'll look more in depth at parallel circuits and see how our equations and behavior change when we wire something in parallel compared to in series like we just did. After that, we'll look at what happens when we have both series and parallel setups in the same circuit.